Hello. So today we're going to talk about units. Units can be very tricky, and it's useful to have some basic skills in how to do conversions between different systems, fundamental to physics and engineering. And when I was an undergraduate, I learnt a very useful technique which helped me to understand how to convert between units, particularly important in aerospace where there are old units and new units kind of mixed. So in units today we tend to think of two main systems, which is metric and imperial, and we can think about mass, length and time, and there's also temperature, and there's other parameters, but we're just going to focus on these for a moment. And in metric, mass is measured in kilograms, length is measured in meters, time in seconds, and temperature in degrees Kelvin. And imperial units, mass is measured in pounds, length is in feet, time is in seconds also, and temperature is in degrees Fahrenheit. Now for temperature, there are some simple conversions you can look up, such as that degrees Fahrenheit is equal to 9/5 times by degrees in Celsius plus 32, or that degrees in Celsius is equal to degrees in Fahrenheit minus 32 times by 5/7. These are useful things to remember, but such conversions don't always exist in a readily usable format, and so it's necessary to have some understanding for how to convert things yourself. Now, a good way to think about units is that you have some input value A, and it has the units of capital A, and it wants to be converted to a new parameter B, which has the units of capital B. So this is an input value, and this is the original unit that you're converting from. This is your new unit that you want to get to, and B is simply your conversion factor. So for example, let's take length, and we know that 1 inch is equal to 2.54 centimeters. Nice and simple. And so what you do is you take your input value A in the units of A, and you're going to multiply this by this conversion in the brackets. And so we know that your units A that you're going from needs to be opposite to the units you're converting. So the A's need to cancel basically. So, and your conversion factors here, and so you end up with the A's cancel, and you end up with A times B in the units of capital B. So using our inch to centimeters example, let's say we had 6 inches, and we want to convert that to centimeters. So we write 1 inch at the bottom because we know we need the inches to cancel, and equals 2.54 centimeters. So this tells us to convert inches to centimeters, we need to multiply the inches value by centimeters, by 2.54. So this becomes 6 times by 2.54 in centimeters, which is simply 15.24 centimeters. Nice and simple. Let's choose another problem, but this time let's deal with mass. So let's say we had a value of 58.25 kilograms, and we want to know what this is in the units of pounds. Well, our conversion is simply that 1 kilograms is equal to 2.2 pounds. And so using our method, 58.25 kilograms times by the conversion in this bracket. 1 kilogram is 2.2 pounds, which gives us 58.25 times by 2.2 pounds is equal to 128.15 pounds, because the kilograms cancel. So that's the trick to always remember, is the unit you're trying to cancel in the conversion, it needs to be opposite to it. Let's deal with another example, another one for length. Let's say we had 1500 feet and we want to know what this is in meters. We know that 1 meter is equal to 3.28 feet, and so 1500 feet times by our conversion, 1 meter is 3.28 feet. This way the feet cancel, which is 1500 times by 1 divided by 3.28, which is equal to 457.31 meters. Nice and simple once again. And so let's build in some other examples. But this time we're going to get a little bit more complicated, and we're going to move to area. So thinking about how our conversion works, we have an original input value A in units of capital A and a conversion factor B in units of capital B, but because it's squared, area is length times length. This is squared and this is squared, but we also have to square the conversion factor. That's what we need to remember. So let's say we had 900 feet squared and we want to know what this is in meters squared. Well, 1 meter is equal to 3.28 feet, and by implication 1 meter squared is equal to 3.28 feet squared. And so we write out our problem. 900 feet squared, we're going to multiply by our conversion, 1 meter squared, 3.28 feet squared, but this time you must remember to square both the unit and the conversion factor. And this results in 900 times by 1 divided by 3.28 times by 3.28, which gives us 83.65 meters squared. What about volume? So we're going up in dimensions of length again. Well, now we have original input value A in units of A cubed, conversion factor cubed, new units B cubed. So let's say we had 2.67 feet cubed, and we want to know what this is in millimeters cubed, just to make it a bit more challenging. So we know that 1 meter equals 3.28 feet, and we know from earlier that 1 meter squared is 3.28 feet squared. Similarly, 1 meter cubed is equal to 3.28 feet cubed. So we write out our number, 2.67 feet cubed, and multiply it by our conversion factor. 1 meter cubed divided by 3.28 feet cubed, which is equal to 2.67 times by 1 divided by 3.28 times by 3.28 times by 3.28, because it's cubed. And this gives us a value of 0.0756 meters cubed. But remember, we need to know what it is in millimeters cubed. We know that 1 meters cubed is equal to 1,000 millimeter cubed, because 1 meter is 1,000 millimeters. And so we end up with 0.0756 meters cubed. Write out our conversion. 1 meter cubed is 1,000 cubed millimeters cubed, and about 1,000 can be written as 10 to the 3, and so we end up with 0.0756 times by 10 to the 3 times by 10 to the 3 times by 10 to the 3, which gives us a value of 756,0000 millimeters cubed. I'm going to add some commas here every 3 zeros. Nice and simple. Let's try another example. We'll use something that has multiple conversions in it. So we'll try density, which is a property we use in physics. And we want to convert, say, 1,800 kilograms per meter cubed into pounds per centimeter cubed. What our conversions will be that 1 kilogram is equal to 2.2 pounds, and that 1 meter cubed is equal to 100 centimeter cubed. So we write out our number, 1,800 kilograms per meter cubed, and we'll write out 2 different conversions now, because we're dealing with 2 different units. So one here and one here. So the first one is going to be for mass, and the second one is for length. So 1 kilogram is 2.2 pounds, so that the kilograms cancel, and 1 meter cubed is equal to 100 centimeter cubed, where we must also cube a centimeter, so that the meters cubed cancels. And 100 can also be written as 10 to the 2. And so our answer is 1,800 times by 2.2 times by 1 divided by 10 to the 2 times by 10 to the 2 times by 10 to the 2. And just to be consistent, we'll add a 1 times here, and this gives us 0.00396 pounds per centimetre cubed. And we will note that we've been using powers of 10 notation, so it's useful just to revisit that. So we've used 10 to the 3 and 10 to the 2, and there's also 10 to the 1 and 10 to the 0, and let's go the other direction, 10 to the minus 1, 10 to the minus 2 and 10 to the minus 3, just so we're clear what these mean. This is 1000, also known as kilo, 1000. This is 100, also known as hecto, or hundreds. This is 10, also known as deca, tens. 10 to the power of 0 is 1, which is the base unit we should all be familiar with. And then we've got 10 to the minus 1, which means 0.1. Being deci, which means tenth. And the 10 to the minus 2 is 0.01, which means centi, which we write as hundredths. And then finally 10 to the minus 3, which is 0.001, which we write as milli, or we refer to as thousandths. And these are all changing by 1 order of magnitude, base 10. We note that the decimal point moves each time. Finally, let's do a physics example of how we might use unit conversions. And we're going to say we've got a problem where there's some neutrons coming out of a reaction. So we're measuring a neutron flux from a reaction in a reactor of some sort. And let's say we're measuring a quantity of 4.613 times by 10 to the power of 23 neutrons per second. And the question is, if 10% of 14 MeV neutrons escape, what is the power in the units of gigawatts? And we're going to assume that there's a 50-50 split in the neutron distribution between 14 MeV neutrons and 2.5 MeV neutrons, which you get from different reactions. And these are the ones we're worrying about most, particularly for a spacecraft, where if they're absorbed into the structure, this requires radiators to re-emit the heat. So we're going to split this distribution. So first of all, we want to do is take 1/2 of 4.613 times by 10 to the 23 neutrons per second, which is equal to 2.3065 times by 10 to the 23 neutrons per second. And we want to work out, first of all, what is 14 MeV in joules. And so we know that 1 MeV, megawatt electron volt, is equal to 10 to the power of 6 electron volts. M standing for mega, just 10 to the 6. And we also know the 1 electron volt is equal to 1.602 times by 10 to minus 19 joules. So that's our conversion factor. So we write this out, and we've got 14 times by 10 to the 6 electron volts. We're going to multiply this by a conversion factor. A 1 electron volt is 1.602 times by 10 to the minus 19 joules, and that gives us 2.2428 times by 10 to the minus 12 joules per neutron. And then the power is given by the neutron flux, which we determined to be 2.3065 times by 10 to the 23 neutrons per second, and we multiply that by this conversion factor for MeV into joules per neutron, 2.2428 times by 10 to minus 12 joules per neutron. And what we notice is that the neutrons will cancel each other out, and this gives us a value of 5.173 times by 10 to the power of 11 joules per second. And since we know that 1 watt equals 1 joule per second, because power is energy over time, we can write that the power is equal to 5.173 times by 10 to the power of 11 watts. Now we need to work out what 10% of that would be. With 10% of this power is 10 divided by 100 times by 5.173 times by 10 to the power of 11 watts is equal to 5.173 times by 10 to the 10 watts. And the final thing we need to do is convert this to gigawatts, and 1 gigawatts is equal to 10 to the 9 watts, because giga means 10 to the 9. And so we've got 5.173 times by 10 to the 10 watts. And here's our conversion. 1 gigawatt is 10 to the 9 watts. So the watts cancel. We're left with a gigawatt unit, which becomes 51.73 gigawatts. So that's the 10% of the 14 neutrons escaping from the reaction into, say, a spacecraft structure, which we would have to factor into any thermal heat management calculations. So that's just a nice, easy illustration of how we use units in physics and engineering problems. That's it.